So this is the outline of chapter 32 about the Maxwell equation. So first of all, we will introduce Gauss law for B fields, and then we'll introduce induced magnetic field and then also the displacement current, okay, which is included in the Gauss law for the magnetic field. Not actually this. This is actually the Ampere's law, the Ampere's law. Okay, so we would like to generalize the Ampere's law into Ampere's Maxwell's law. So we will have something called the displacement current. And then for the later part, it is some kind of hardcore physics or it relates to some of the phenomena in the Earth. So let's try to somehow listen to it, pretending to, so you can regard it as listening to a story. Okay, so first we'll introduce the Gauss law for magnetic field. So as I mentioned before, in the world we don't have magnetic monopole. Magnetic monopole do not exist. Okay, so in such a way, for the so actually this is actually the Gauss law for B field. So we only have zero on the right side. So comparing with the Gauss law for the E field, it somehow like you change E into B. And then you change epsilon naught, as I mentioned, you change epsilon naught into 1 over mu naught. So mu go to numerator. But for the E field, we can have positive charge or negative charge. But for the B field, we don't have any magnetic monopole. It always comes with a magnetic dipole. Okay, so if you add the magnetic charge, okay, the dipole, okay, the positive and negative always cancel. So it's somehow like mu zero multiplied by a zero magnetic charge. Okay, so it turns out to be a zero. So in such a way, we don't have mu naught here because mu naught is a non-zero term. We just cancel it. We only have this magnetic flux for a Gaussian surface to be zero. So it will be even more easy to use because we don't need to consider the Q enclosed for the B field. Okay, so next is the induced magnetic field. Okay, so in chapter 30, we have already learned the induced E field. Induced E field is actually the induced EMF. Is the induced EMF. So if we have a changing magnetic flux, it will generate induced E field or induced current. Okay, so in here we also have, if we have changing electric flux, it will also generate B field. Okay, so comparing with the Faraday's law, it is something like in integral of E dot ds equals negative d phi b dt, or if you like, you can also multiply n here, okay, to make it something like this, or you may also absorb this n into the phi b, so it look more elegant. So it turns out to be something like d phi b dt, something like this. Okay, so this is the Faraday's law. This is the actually so-called the Maxwell's law. Okay, so it also says in the time varying E field will generate B field. Okay, something like this. Okay, so here we have some constant mu naught epsilon naught here. Okay, so of course the epsilon naught and mu naught are the permittivity and the permeability 就是两个很重要的常数，就是那个电导率跟磁导率。epsilon naught 就是那个电导率，那 mu naught 就是那个磁导率。 OK， 那么它们乘起来的话，它会跟一个很重要的常数有关啊，当然不是 mu not 乘 epsilon not 本身，是一除以开根号这个数啊，一除以开根号这个数才是那个重要的常数，那个常数叫做光速，叫光速啊，所以光就是那个电磁波嘛，所以它就会跟这两个电池的重要常数有关。Okay, so so here it just mentioned that the charge on a capacitor is being increased at the steady rate by a constant current I in the connecting wires. So actually we have a capacitor here, and if we have a constant current charging this capacitor, so it means that we will have Q to be increasing. This positive Q and negative Q here is actually increasing at a steady rate. So in such a way, we will have increasing E field also in a steady rate, because this E field is something like sigma over epsilon naught. Epsilon naught is a constant, and sigma is the charge density. If this charge amount is increasing in a steady rate, this sigma also increase in a steady rate. So in such a way, this E field also increase at a steady rate. So in such a way, we can also consider d phi E. Phi E is the electric flux. So the electric phi E is actually integration of E dot dA. We don't have this circle here. The surface is only this cross section. It's only this cross section. So we don't have a circle here. It's not a closed surface integral. It's just a normal surface integral. So if E is increased in a steady rate and uniform distribute, so this phi E also increases at a steady rate. Okay, so if this is increased in a steady rate, so d phi E dt will be a constant. So this whole thing will be a big constant. Okay, so which means that it will generate. This is the line integral of the B field. So in such a way, this one is actually the cross section for this capacitor in between. Okay, so you can consider this is the cross section, okay, which is this one. Also, you consider this capacitor is a circular plate, okay, 是一个圆形的，两面都是圆形的。那所以我们这个 cross section 是这个东西。那 okay, so in such a way, E field is pointing into the page. If this E field is increased in a steady rate, it will generate B field clockwise. Okay, so this is clockwise. 为什么？又是 right hand rule， 就是右手法则。那你用你的拇指指上你的 E field 的方向，那你另外几根拇指的话，你就会是顺时钟的方向。Okay, so you still use the right hand rule to know the direction of the induced B field. So then the electric field magnitude between the plate must also be increasing at a steady rate. And then because the electric field through the loop is changing, the electric flux through the loop must also be changing. So according to the above equation, this changing electric flux induces a magnetic field around the loop. Okay, so this is just what I've mentioned. Yeah. And here we also assume that the E fields between the plates are uniform. So this generated B field are also uniform if the distance from this point to the center is a constant. So which means that if we have this Amperean loop, we will consider the B field over this whole path are uniform. So in such a way, for this case, this integration of b dot ds is nothing but b times 2 pi r, just as what we did before. Okay, so here it tried to compare this Maxwell's law with the Faraday's law. Maxwell's law with the Faraday's law. So actually, they are similar in terms of we have some time varying E field, it will generate B field. Here, if we have a time varying B field, it will generate induced E field. But there are two different in two ways. So the first one is we have mu naught and epsilon appear for matching the SI unit. Okay, so this one is related to the speed of light. Okay, so the speed of light c will be 1 over square root of mu naught epsilon naught. 那这个值的话是2997meter per second. OK， 所以是这个数，299792458 OK meter per second。那这个数的话，其实正常的情况我们会是3乘以10的八次方。Usually we will use 3 times 10 to the 8th power meter per second, or in some of the modern physics, they will use 2.998 times 10 to the 8 meter per second. 就是比如说相对论的话，他们会用2.998乘以10的八次方，或者是量子力学会用到吗？比较少，就是通常的话就是相对论，或者是一些光学optical， 他们也会用2.998，不然的话平常都是用3乘10的八次方。Okay, so and then the next point is that the negative sign for the Faraday's law means the induced E field is counterclockwise if the B field directly into the page is increasing. Okay, so the point here is if we have just as what we mentioned. Okay, so this E field, induced E field, this external E field is increasing and pointing into the page. So the B field, so the induced B field is clockwise, just as this one. Okay, because we have a positive sign. We have a positive sign here. But here we have a negative sign for the Faraday's law, which means that if we have B field pointing into the page and then it is uniform and then increasing in a steady rate, the induced E field is counterclockwise. Okay. So this is what this negative sign tells us. And of course in chapter 30 we learn this negative sign as Lenz's law. Okay, if you still remember Lenz's law. Okay, so these are the two differences for the Maxwell's law and Faraday's law, and otherwise they are quite similar and they are the derivative. Okay, so just like changing E to B and then changing B to E, but we have also this concept to match the SI unit. Okay, so in chapter 29 we know the Ampere's law. And then we know that this line integral is mu naught times I enclosed. Okay, so this is a static current, which means if we assume it is a constant current, okay, we will use this. And here we also have this Maxwell's law. Okay, have this same line integral with a derivative on the right side. Okay, so the question is why not both? We make it like this is the line integral equals to this. This term is due to the static current, and this is due to the changing E field. Okay, so both of them will generate induced B field. Okay, or actually generate B field. Okay, generate B field. So here we will just call this one Ampere-Maxwell's law, or for some literature they will just call the whole thing the Ampere's law. So it just depends whether you want to put Maxwell's name on this law. because the contribution is that this term is proposed by Maxwell. Okay, Ampere proposed this one. Okay, so yeah, so yeah, you can consider it as a generalized Ampere's law, or you can call the whole thing Ampere's Maxwell's law. It is somewhere a big problem here. Okay, so here it says when there is a current but no change in electric flux, then the first term on the right side will be 0. And so the equation reduced to Ampere's. So the first term, I think it should be, second, the second term. Okay, 就是说，如果只有一个电流的话，没有电场的改变的话，就第二项会变成0，它就会缩减到成为一个 Ampere's law. So when there is a change in the magnetic flux but no current, the first term, okay, the first term on the right side of the equation is 0, and so the equation reduced to Maxwell law of induction. Okay, 就是如果没有电流的话，第一项就会变成0，就会变成 Maxwell law. 所以我们一开始的话就两个都写我们就看有没有其中一个或者两个都同时出现。如果什么都没有的话，当然就没事发生。那如果有一个的话，我们就看哪一个。那也有可能是两个都有的话，也有可能吧。Okay, so here we have a sample problem. Okay, so here it says a parallel plate capacitor with a circular plate of radius r is being charged. Derive an expression for the magnetic field at radius r for the case r is smaller than or equal to capital R. Okay, so here we have we only have a change of electric flux, so we can simply consider the Maxwell's law. So integration, the line integral of B dot ds is mu naught epsilon naught d phi e dt. Okay, so this is mu naught epsilon naught d phi e is actually e times a. Okay, we just consider these e and a are parallel to each other, and also e is uniform over this cross section area. Okay, so we have this phi e to be e times a only. Okay, so actually this line integral, we can also consider b is uniform, and also b is parallel to the tangent line of this path. So this simplified to b times 2 pi r, and then equals mu naught epsilon naught, and then the a doesn't change, so we can put a outside, and then we have a de dt. Okay, so actually mu naught epsilon naught, and then a is the cross-section area of a circle, so this is nothing but pi r square. Okay, so and then times de dt. Okay, so we also put this b times 2 pi r here. Okay, so here we can do some cancellation. We cancel this r with this r square, and then we cancel this pi with this pi. So finally, b is actually mu naught epsilon naught over 2 times de dt. Okay, so this is the closed form solution for this B field when R is more than or equal to capital R. Okay, so it asks you to evaluate the field magnitude B for R is equal to capital R over 5 and dE dt equal to this value. So we can just substitute the number into it. Okay. So mu naught is 4 pi times 10 to the 7th power. And then E is 8.85 times 10 to negative 12. And then times R is 11 millimeter, 11 times 10 to negative 3rd power, all over 2, and then times dE dt is 1.5 times 10 to the 12th power. Okay, so this is 9.18 times 10 to negative 8 Tesla. Okay, so you just put the number in the formulas, and then question C, derive an expression for the B field when R is larger than capital R. Okay, so here we consider the Ampere loop is something like this. Okay, so here we still have integration of B dot ds equals mu naught epsilon naught d phi e dt, and then it is also mu naught e naught, and then a times dE dt. Okay, we just give you the steps because the previous steps are actually the same with the previous case. So here is the difference. For the B, for the left side, the integration of B dot ds is still B times 2 pi r. Okay, for regarding to this path. But on the right side, it is actually mu naught epsilon naught. This A we just consider up to this part. Okay, so the outside part we don't have any E field. We just assume there's no E field outside this part. Okay, so for the cross-section area, we only count up to here, which is capital R. So here for the cross-section area is a pi capital R squared, and then dE dt. Okay, so here we can only cancel the pi, we cannot cancel R. So here we have a B equals mu naught epsilon naught over 2, and then times capital R squared over small r, and then times dE dt. Okay, so this is the expression when R is larger than capital R. Okay. Okay, so here we will talk about the displacement current. Okay, 中文叫做位移电流，位移电流。Okay, okay, so it says if you compare the two terms on the right side of the equation, Ampere Maxwell's law, you will see that the product, this one, must have the dimension of a current. In fact, the product has been treated as being a fictitious current. Fictitious 就是一个是幻觉的，就是虚幻的一个电流 called the displacement current。那个意思是，回到这边吧。这边的话，what you can do is actually to factor out mu naught. Okay, so this is the only common factor. So we have mu naught, and then I enclose, and then plus epsilon naught d phi e dt. Okay, so it says this is a current. This is a current. So these terms should also have a dimension of a current. And yeah, so this is somehow similar to a current. So in fact, that product has been treated as being a fictitious current called the displacement current ID, which is this term. So if you define this one to be ID, the Ampere's Maxwell law can be written as this one equals mu naught I enclosed plus mu naught ID enclosed. Okay, ID enclosed, or you can just consider it ID enclosed, or you can just write it as a mu naught I enclosed plus ID enclosed。那所以这个虚构的电流是什么？简单来说的话是电容的电流，它是一个电容的电流。The current of a capacitor. Current of a capacitor. How do we know this is a current of capacitor? So if we just try to write ID is epsilon naught d phi e dt, we can actually verify it with some simple calculation. Okay, so actually we have epsilon naught and then d ea. Okay, so phi e is e times a, and then we try to put this a out. Okay, epsilon naught and then times a and then de dt. Okay, so here we try to divide this thing by d and then also multiplying this thing by d. Okay, so it just these two d just cancel each other, so we don't make any change to this whole formula. Okay, so a over d, epsilon a over d is very familiar. We are quite familiar with this thing. This is actually C. This is actually C. The parallel plate capacitance, if you still remember in chapter 25. Okay, so we try to form this is the capacitance. And here, this E times D is actually the voltage or the potential difference. Okay, so we have a dV dt. Of course, we just assume all the things to be uniform to make things easy, just like calculating some algebraic things. Okay, so it turns out to be this ID, this displacement current is C dV dt. Okay, so this is actually the current of a capacitor. Actually, the current. 所以他说他虚构的原因是其实我们也会定义这个电容的电流，但是其实这个电荷有没有真正通过这个平行板呢？是没有的。其实它只是说我有电流进来，那它会有 Q 累积，那负 Q 就会在另外一边累积，它同样会有 I。它其实 I 是没有穿过它，但是 I 也没有断下来。那如果你要反方向流的话，也可以啊，我 I 也可以往反方向流去 discharge 也可以。所以我们就把这个 I 也当做这个电容的电流，或者是物理上它就叫做 displacement current， 它就好像穿过它一样，那实际上的话是这里累积了电荷。Okay, so here we also have some formula with displacement current. You can also derive if this thing is R is larger than capital R, we have this one. So it is just as the same as the one we get in chapter 29. Okay, in chapter 29 we also have this one. this B field is due to a static current. Okay, we also have this formula. But here, if we have displacement current for capacitor, we still have the same expression if R is larger than capital R. And here, if R is smaller than or equal to capital R, we have this expression. This B is proportional to R. And yeah, so yeah, actually we already derived it before. So I don't try to repeat it. You can try to practice it by yourself. You can still get this one. If you just assume there is time varying E field changing, time varying E field changing, there will be generate B field. Okay, so here we have a sample problem. So it says the circular parallel plate capacitor is being charged with a current I between the plates. What is the magnitude of this integral in terms of mu naught and I at radius r equals to capital R over 5 from the center? Okay, so this integration of B dot ds is actually mu naught ID enclosed. So actually, when we need to consider this ID enclosed, and we also consider the current density. The current density is uniform. So we have ID enclosed over ID is actually pi r square over pi capital R square. Okay, so this ID is for the whole current. Okay, it's the whole current, and then this ID enclosed is only enclosed by the circle with a smaller radius. Okay, so we have pi r square over pi capital R square. So they are the cross section area. Because actually you can consider it's like multiplying by the same current density. So this J and J cancel each other. So finally it turns out to be R square over capital R square. Okay, so it means that ID enclosed is actually ID times R square over capital R square. So in such a way, we can put this one back to here, which means integration of B dot ds equals mu naught times ID times R square over capital R square. And then here we have this small r equals to capital R over 5. So here we have a mu naught times ID times capital R over 5 quantity square over R square. So which is mu naught ID over 25. Oh, this ID is nothing but I, so we can write it as mu naught I 25. Okay, so here we still have a question B. So it asks in terms of the maximum induced B field, what is the magnitude of the B field induced at R equals R over 5 inside the capacitor? Okay, so it means that B of R is actually mu 0 I D or I over 2 pi R square times small r. Okay, just as what we have actually using this one. Okay, so which means that it is actually proportional to R. So it means that if R equals to capital R, it will be maximized value. So B max is actually B capital R. Because this is only true when R is smaller than or equal to capital R. Okay, so later on, if R is larger than capital R, then it will decrease again. So in such a way, BR over B max will be BR over 5 over BR. So it will be nothing but 1/5 because this is proportional to R, this is proportional to R, so this is proportional to R over 5 over R, so it is 1/5. So which means BR will be 1/5 of B max, 1/5 of B max. Okay. Okay, so here is a quick summary for the Maxwell equation. So actually we have two Maxwell's law. Okay, one is for electricity, one is for magnetism. So this is what we learned in chapter 23. Okay, and then this one we learned it in this chapter 32. Okay, so on the left side is a flux. Okay, either the electric flux or the magnetic flux for the closed surface. Okay, for the electricity version, we have Q enclosed over epsilon naught. Okay, but here we don't have a magnetic monopole, so we have a zero on the right side. So Faraday's law and Ampere-Maxwell's law are the other pair. Okay, so here we have induced B field generate E field, and for the Ampere-Maxwell's law, we can have time varying E field generating B field. We can also have static current generating B field. Okay, if we want to have B field, E field generating each other in a loop, we actually need to starting from time varying B field and time varying E field. So time varying E field will generate B field, and then it will be a time varying B field. This time varying B field will generate time varying E field again, and then going back to here, and then loop back and forth. But if we only have a static current, it will only generate static B field. This static B field won't generate E field because the derivative of a constant is a zero. So this one won't go through this infinite path. Only these two terms will just make these two formulas loop back and forth forever. And actually we learned this in chapter 30. This is chapter 29 and 32. Okay, we have learned the Maxwell's equations. Okay, so actually using these four equations explain a diverse of range of phenomena. They are basis of functioning such as EM device, such as electric motor, transmitter, receiver. Okay, something like the wireless transmission, telephone, scanner, radar, microwave oven. OK， 那就是这个是所谓的积分形式的Maxwell equation。实际上有一个叫做微分形式的Maxwell equation， 那书上面没有讲。那我讲完这一课之后会补充一下，也让你们知道。那些数学的话，就是稍微比较难一些，但是可能跟一些流体力学的数学会有点相近啦。那所以会讲一下。那实际上如果要用 Maxwell equation 来处理其他事情的话，其实有用的是微分形式，因为它是微分形式是一些微分方程嘛，所以可以用一些数值的方法去得到一些解。那积分形式的话，它正常是没什么用的，有用的只是用来手算，所以这是只是对考试有用，所以课本上只有这个积分形式。